In the last section, we had taken a look at how 4 momentum eigenstates for massive particles respond to parity and time reversal operations. In today's part, we are going to talk about a similar thing, but for massless particles. But let me quickly remind you of what we found in the massive particle case. Remember, for massive particles, the standard 4 momentum that we had was that for a particle at rest. This, of course, is something that's going to change for massless particles, because as you all know, massless particles can never be at rest. They always move with the speed of light. But for massive particles, this was the standard 4 momentum. And then we had a standard Lorenz transformation which actually carried this 4 momentum to the momentum p. And the first thing that we looked at was how parity and time reversal, these two respectively unitary and anti-unitary operators, act on the standard momentum eigenstate psi k sigma, where sigma of course is a J3 eigenstate. And we figured out from the fact that parity actually keeps the standard 4 momentum intact and also sigma intact, you must get psi k sigma times a phase factor which could depend on sigma, which we subsequently showed was independent of sigma. So we ended up with essentially something called the intrinsic parity. We did a similar analysis for time reversal, and there we figured out that since time reversal also does not change the standard k, but changes the J3 component, what you would get is psi k minus sigma times a phase factor, which we figured out had to be of this particular form. We then went on to talk about psi p sigma, which was momentum eigenstate for arbitrary momentum, which, remember, apart from a normalization factor, was basically u of L of p acting on psi k sigma. And then we talked about the interplay between the parity operator and u of L of p and the time reversal operator and u of L of p, and figured out exactly how the state psi p sigma responds to parity and time reversal. We are going to do something very similar in this lecture, but now we are going to talk about massless particles, so things are going to be slightly different there. Let me remind you that for massless particles, the standard 4 momentum k was taken to be of the form kappa 0 0 kappa, that is, a particle which is moving along the z-axis, of course with the speed of light. And the standard Lorenz transformation in this case, which would carry this kappa 0 0 kappa to the final 4 momentum p of the particle that we are interested in, had this particular form, r of p hat times b of mod p hat by kappa. So mod p hat by kappa is basically a dimensionless parameter which we call u, and this b of u essentially boosts the particle whose momentum was kappa to begin with into a particle whose momentum magnitude is given by mod of our final momentum, and which is exactly in the z direction. So this is just a boost in the z direction, and the particular matrix that describes this is on your screen right now. After applying this particular boost so that the momentum of the particle comes out to have the correct magnitude, you then apply a rotation which would carry the unit vector along z into the direction of p hat. Now this particular rp hat that we have chosen, and this is something where we have to make a specific choice because there are infinitely many available, is described in the following manner. Strictly speaking, this is not r of p, this is actually u of r of p hat, the corresponding unitary operator, And this describes the rotation about the y-axis to an angle theta, actually minus theta, and followed by rotation about the z-axis through an angle minus phi. Here theta and phi are the polar and azimuthal angles which describe the vector p hat in the final coordinate system. Why minus theta and minus phi? I had explained that earlier when we talked about the behavior of massless particles in some detail. And let me just remind you that this has to do with the fact that the rotations that we are talking about here are passive rotations, rotations of the coordinate system, not of the actual vector. And for definiteness, what we have done is we have restricted theta and phi to the ranges shown here. Theta is between 0 and pi, and phi is between 0 and less than 2 pi. The reason why specification of this range for theta and phi are important is the fact that if you are dealing with half-odd integer spin particles, changing phi by a full 2 pi, which would give you back the same point, still gives you a different u of r. And this is something which has to do with the fact that the rotation group is not simply connected. This topological fact is something we are going to discuss in some more detail in a later lecture. I must confess that I was guilty of using active mode language, if you know what I mean, a while ago, when I should have actually used passive mode language. This was when I said that the momentum of the particle is being boosted to its final value. Of course, what is really happening is that you are going over to a new coordinate system in which the momentum takes on a new value. The particle, of course, does not change. It's the same as always. Proceeding along the same lines that we had followed for massive particles, what we are now going to do is take a look at what parity does to the state psi k sigma. Of course, psi k sigma was an eigenstate of H, the three components of spatial momentum, and J3 with eigenvalues kappa, 0, kappa, and sigma respectively. And what we are going to do is take a look at what these same operators H, P vector, and J3 do to the state parity acting on psi k sigma. So H acting on P psi k sigma is pretty straightforward. We have already figured out earlier that parity and Hamiltonian must commute. And let me remind you once again that this is what led us to the conclusion that the parity operator is a linear unitary operator. And that means that the eigenvalue kappa will be the same for P psi k sigma as well as the original psi k sigma for the Hamiltonian. As far as P vector is concerned, the momentum vector anti-commutes with parity, and this introduces a negative sign. So you are left with a set of eigenvalues minus 0, kappa for P psi k sigma. And J3 commutes with the parity, and therefore J3 has the same eigenvalue for P psi k sigma as it had for psi k sigma, namely sigma itself. So what we see is P psi k sigma is a simultaneous eigenstate of P mu and J3, just like the original psi k sigma was, with eigenvalues given by the parity reversed version of the 4 momentum k, kappa 0, minus kappa, and for J3 the eigenvalue is sigma, the same as for the original state psi k sigma. So this brings us to a very, very important conclusion. The helicity, the component of the angular momentum in the direction of the momentum, gets reversed under the action of parity. J3 stays the same, but the momentum reverses. So the component of the angular momentum in the direction of momentum has changed its sign. Now this is very, very important because what we had already seen for massless particles earlier is that when you go from one inertial frame to another, the spin or sigma 3 eigenvalue, helicity, for a massless particle does not change. However, as we have just seen, parity reverses the helicity of the state describing a particle. Now, This led us to the conclusion that if parity is a good symmetry for a particular system, then what we should do is regard these two states with sigma values of plus sigma and minus sigma, these three eigenvalues, as two states of the same particle rather than as two different particles, despite the fact that none of the continuous Lorenz transformations actually changes the helicity of plus sigma to minus sigma. For particles which take part in interactions for which the weak interaction is not a symmetry, this conclusion no longer works, and then particles with opposing helicity should be treated as different particles, as we did, for example, with the neutrino. Note that for massive particles, k mu, the standard form momentum, did not change under the parity operation. Neither did sigma, the eigenvalue of J3. This helped us to identify P acting on psi k sigma as the state psi k sigma itself with an overall factor, the so-called parity quantum number. Now the problem with massless particles is the standard form momentum here is kappa 0 kappa, and that does not stay unchanged when you carry out the parity operation. It changes to kappa 0 minus kappa. Now since this would make things a bit more complicated, what we would prefer is an operation which is related to the parity but which does not change the standard form momentum. And that's pretty easy to figure out. All you do is think of another Lorenz transformation, in this case a rotation, that will also take k mu, the standard form momentum, to the parity reverse version of the standard form momentum kappa 0 minus kappa. Now there are infinitely many rotations that will do the job, but the most convenient one that is chosen, and that's actually indicated by the name R2, is actually a rotation through pi about the 2 axis. So basically what we are going to do is, since R2 carries the standard form momentum k to the same final result as does parity, R2 inverse parity carries k back to itself. So what we are going to do is, instead of talking about parity, the curly p Lorenz transformation, we are going to talk about R2 inverse curly p, and when we talk about operators acting on Hilbert space, we are going to talk about their operator version u of R2 inverse, u of curly p, or u of R2 inverse capital P. Now at this point you may actually be surprised that we are talking about u of R2 inverse here, simply because a rotation through 180 degrees is self-inverse. So R2 inverse and R2 are actually the same rotation. However, let me remind you once again that for spin half particles for which sigma takes a value of half odd integer, u of R2 inverse and u of R2 are actually different, so we have to be a bit careful here. It should be pretty easy for you to figure out that R2 inverse parity is nothing but a reflection in the xz plane. And one immediate consequence of this would be that this reverses the third component of angular momentum, or in terms of the operators, u of R2 inverse p must anti-commute with J3. Thus, while u of R2 inverse p leaves the eigenvalues of p mu for the standard momentum kappa 0 kappa unchanged, it changes the value of J3 to minus sigma. So u of R2 inverse p acting on psi k sigma is a state which we must identify with the state psi k minus sigma with a phase factor eta sigma, multiplying it possibly. Now, unlike the case of the massive particles where we had the full power of the SO3 algebra, which helped us to actually figure out that eta sigma was independent of sigma, here we don't have any such recourse, for the simple reason that a given particle would be described not by a multiplet of different sigma values, but with just two sigma values, sigma and minus sigma, so we don't really have much to do here. Our next job would be to try to figure out what parity operator does to psi p sigma, where psi p sigma is a general momentum eigenstate, 4 momentum eigenstate for a massless particle. Let me remind you that psi p sigma is root over m by k0, the normalization factor, and k0 of course is just kappa, times u of L of p acting on psi k sigma, and L of p, as we just described a while ago, is a rotation rp hat preceded by a boost along the z-axis. So when p goes and acts on this, you remember that p, the parity operator, is nothing but u corresponding to curly p, and we have assumed that such an operator exists. Let me remind you once again that for systems for which parity is not a symmetry, the existence of such an operator is, well, at best an approximation. But for the time being, we are assuming that such an operator exists, and essentially the standard composition rules for Poisson transformations keep on working here. That's also an assumption that we are making. So the parity operator can of course be moved inside the u in the form of u of curly p. And now we come to the very important point that parity actually commutes with this particular rotation that we are going to talk about, which brings the unit vector along the z-axis to the final direction. Now since parity commutes with rp hat, we can flip it across rp hat and get to this stage, where the unitary operator is the unitary operator corresponding to rp hat curly p, then the boost. Of course, the order in which the operators act is the opposite. Boost gets to act first, then the parity operator, then the operator corresponding to rp hat. Now, curly p, on the other hand, the parity operator does not commute with boost along the z-axis, as you can easily check. However, R2 inverse curly p, which is nothing but a reflection in the xz plane and hence only affects the y-axis, and the boost of course only affects time and z, the two commute with each other. So what we can do is supply in the form of an identity and R2 inverse here, and then take the R2 inverse curly p right across the boost and make it act directly on psi k sigma. So we are left with a new operator inside rp hat R2 and the boost, and then you have u R2 inverse p acting on psi k sigma. We already know what u R2 inverse p acting on psi k sigma is. It gives you psi k minus sigma and a factor of eta sigma, which is just a number, so we'll move it outside. And remember, we are all dealing only with linear operators here. Now the question is, exactly what is this new Lorenz transformation rp hat R2 times boost mod p by kappa? To see this, let's figure out what rp hat R2 b mod p by kappa will do to the standard 4 momentum. The boost, which will act first, will give you a momentum with the right magnitude mod p vector along the z-axis, but R2, a rotation through 180 degrees about the y-axis, will now flip it over to minus the z-axis. And then when you apply the final rotation, it will obviously carry this final vector not to the direction of p hat but to the direction of minus p hat. So finally you get a momentum which has the right magnitude and the right direction but the opposite sense. So instead of ending up at p vector, you end up at minus p vector. Of course, all this, the two rotations, do not affect the zeroth component of the 4 momentum at all. So you end up with root over p square plus m square as the zeroth component of the 4 momentum as before. And this is nothing but what the parity, the Lorenz transformation, does to p. So this particular combination of Lorenz transformations, rotations and boost that you have here is a Lorenz transformation which carries our standard 4 momentum k to curly p p. But the question is this the same as a standard Lorenz transformation which will carry k to curly p p? That is, is this the same as L curly PP, whose corresponding unitary operator acting on psi k sigma will give me psi curly PP comma sigma? The answer actually is no, as we will see now. Let me remind you that according to the prescription that we have been following, the standard Lorenz transformation which carries k to curly PP has to be the following. You must first boost the momentum kappa to the final value mod p vector by a boost along the z-axis. This is the same as the one in L of p, but then the rotation that you have to carry out must carry the z-axis into minus p hat and not plus p hat. And once again, we have to be careful about exactly what this rotation is. Remember, we need to first figure out the polar and azimuthal angles which describe our final destination and use that to figure out the corresponding u of r of minus p hat. Now first, what are the polar and azimuthal angles describing minus p hat if theta and phi are those describing p hat? Now this is something which we have actually studied earlier in several places, maybe in quantum mechanics when we talked about the action of parity. But the basic idea is that under parity, p reverses to minus p, as you can see here. For minus p hat, the polar angle is of course this one, which is pi minus theta. Now what about the azimuthal angle? You need to turn the xz half plane, which had to turn through phi to go through p hat, by an additional angle pi. So we usually say that the azimuthal angle for minus p hat will be phi plus pi. However, we have to be very careful here. Remember our limits on theta and phi were theta had to be between 0 and pi, which is valid for pi minus theta. So there's no problem there. But phi has to be between 0 to 2 pi. So now you have to be careful. Is it going to be phi plus pi or phi minus pi? That depends on which one of the two is within 0 to 2 pi. It's very easy to see that if the py component were positive to begin with, then a rotation through an additional pi will keep the value of phi within 2 pi. So if py is positive, the azimuthal angle for minus p hat will be phi plus pi, and if py is negative, you are already on the other side, that is, you already have to go through an angle which is more than pi in order to turn the xz half plane to the p vector. Then an additional plus pi would have taken you out of the 2 pi range. Then you would have to actually subtract 2 pi from that result, and so your azimuthal angle there would be phi minus pi. So the polar angle is always pi minus theta, but the azimuthal angle is phi plus or minus pi depending on whether the original y component of the momentum was positive or negative. So now let us take a look at the two standard rotations, or rather the corresponding unitary operators. U r of p hat, of course, as we had already seen earlier, is e to the minus I phi j3 e to the minus I theta j2. And then of course you have u r2, this particular operator, which is e to the I pi j2. We must remember that. And u of r of minus p hat has to be e to the minus I phi plus minus pi, plus or minus depending on whether py is positive or negative, times j3 times e to the power minus I pi minus theta j2. So in order to see whether our rotation r of p hat r2 is the same as r of minus p hat, what we need to do is simply multiply u of r of p hat r2 by u inverse of r of minus p hat. If the two operators were one and the same, then these should cancel each other out and you should get the identity. The question is, do we really get the identity? And that's pretty easy to figure out, because u inverse r of minus p hat is simply to the plus I pi minus theta j2 times e to the plus I phi plus minus pi j3. Then you have u of r of p hat, which is e to the minus I phi j3, e to the minus I theta j2. And finally, you have u of r2, which is e to the I pi j2. So collecting the j3 terms together, that is cancelling out the e to the I phi j3, you simply get e to the I pi minus theta j2 times e to the plus minus I pi j3 times e to the I pi minus theta j2. Now from the fact that a rotation about the z-axis to an angle of 180 degrees reverses the y-axis, it follows rather simply that e to the plus minus I pi j3 and j2 anti-commute with each other. And an immediate consequence of this is that if you were to take e to the plus minus I pi j3 right across this operator, it's going to change the sign of j2 here, and you're going to be left with this combination. E to the I pi minus theta j2 here stays the same. This e to the I pi minus theta j2 becomes e to the minus I pi minus theta j2, and of course the e to the plus minus I pi j3 has moved to the other side. So these two operators simply cancel, and we do have a lot of cancellations, but you don't end up with the identity, you end up with e to the plus minus I pi j3. So u of rp hat r2 is not exactly u of r of minus p hat, is really u of r of minus p hat times e to the plus minus I pi j3. Let's resume our discussion on what parity does to psi k sigma. Remember, what we had at this stage was this parity constant number, eigenvalue eta sigma, has come out. You have root over m by k0 or p0, whatever you want to call it. Then you have u of r of p hat r2 times the boost acting on psi k minus sigma. U of r of p hat r2 is nothing but u of r of minus p hat e to the plus minus I pi j3. And now notice the fact that this rotation about the 3-axis changes only the x and y coordinates, whereas the boost changes only the t and the z. So they commute with each other. So you can safely move the e to the plus minus I pi j3 right across the boost operator, bring it here. And now, since psi k minus sigma is an eigenstate of j3 with eigenvalue minus sigma, this simply gives rise to an extra factor of e to the minus plus I pi sigma. And therefore, the overall result simply becomes eta sigma e to the minus plus I pi sigma, this factor coming right out, into root over m by p0, but you can also write p0 as curly p0. After all, curly p, the parity operation, does not change the zero component of the force momentum at all. U of L curly pp acting on psi k minus sigma, and this obviously is nothing but the state psi curly pp comma minus sigma. So our overall result is simply this: when parity acts on a momentum eigenstate of a massless particle, you end up with an overall factor of e to the sigma times another extra phase factor e to the minus plus I pi sigma, and the state corresponds to the parity reversed momentum. Of course, only the spatial part reverses, the temporal part stays the same, and reversed spin eigenstate minus sigma. Now one thing might worry you a bit here, and that is the presence of this extra phase factor e to the minus plus I pi sigma. There is nothing wrong with having an extra phase factor, except that the sign of the phase here depends critically on the value of, or rather the sign of py. If py is positive, you end up with e to the minus I pi sigma. If py is negative, you end up with e to the plus I pi sigma. And that means that if you have two momenta which are very, very close to each other but right on the opposite sides of the xz plane, the parity operation gives you two opposing phase factors for that. And that might sound very, very unexpected. However, as we had already pointed out earlier when we talked about the states for the massless particle, especially how they respond to rotations, we had pointed out that you would expect such trouble here for the simple reason that the spherical polar coordinate system that we are using has coordinate singularities on the z-axis. And so states which are just very close to it but on opposite sides are designated very, very differently as far as the overall phase is concerned. And therefore, you end up with this rather unsavory looking phase factor. We have to live with it as long as we are using the spherical polar coordinate systems. But that doesn't really mean the states on two sides of the xz plane are very, very different from each other as far as the behavior under parity is concerned. If you take into account the way in which we define the parity of the states psi curly pp minus sigma, in the two cases you would see that the action of parity on two states with very close initial momenta always stays very close to each other. Now I just realized a while ago that I have made a rather stupid but in the end inconsequential error in the calculations above. Actually, that's sort of obvious. This m here is definitely not a part of the normalization factor. After all, we are dealing with massless particles. So, the numerator here is not m, the mass, which obviously is 0, but rather the initial value of P0, which in this case is kappa. So, all these factors, in fact not only this one, all the previous ones in this whole calculation that you can see, all of these starting right from the initial statement that we made here should really be reading root over kappa by k0. But ultimately, that is not really a big deal because that factor gets absorbed in your final result anyway. The final result that we talked about is perfectly alright. Let us now try to describe the effect of time reversal on massless momentum eigenstates, and we will start as for parity with psi k sigma, that is, with states with a standard 4 momentum. Now it's very easy to see that T acting on psi k sigma is a simultaneous eigenstate of the 4 momentum p mu and j3, and now once again the eigenvalues have changed. The corresponding eigenvalues of p mu is kappa 0 0 minus kappa, and for time reversal, sigma also changes to minus sigma. Note that the time reversal operation does not change helicity. So, just because something is time reversal symmetric does not connect a state with positive helicity with a state with negative helicity. It's only parity which does that. But very much like parity, time reversal also does not leave the standard 4 momentum invariant. In fact, it changes it to the same final 4 momentum kappa 0 0 minus kappa. So the remedy is very similar. Instead of talking of the time reversal operator on its own, let's talk about u of R2 inverse t. And when that acts on psi k sigma, what that does is that it gives you back the same standard 4 momentum k by reversing the minus kappa back to plus kappa. That's what a rotation about the y-axis to 180 degree will do. But it also changes the minus sigma component for J3 back to plus sigma. So, UR2 inverse T psi k sigma is essentially psi k sigma with a possible overall factor zeta sigma. Once again, the question about how zeta sigma changes or whether it does not change with sigma is not really very important, because for massless particles, you don't really have a multiplet of different sigma values. Now, what we are going to do next is talk about what time reversal does to psi p sigma. And for that, again, we look at R2 inverse curly T, the time reversal operator. This commutes with the boost, mod p vector by kappa, while curly T commutes with the rotation Rp hat, just like the curly P did. Time reversal operator T acting on psi p sigma will be U of curly T, acting on the standard root over kappa by P0 times U of Rp hat B mod P by kappa, psi k sigma. And then we will move the curly T across inside, and then in order that we can move R2 inverse curly T all the way out, we introduce the identity here in the form R2, R2 inverse. Then move R2 inverse curly T all the way out in the form U R2 inverse capital T. That gets to act on psi k sigma. But you have also this R2 left inside as before. So once again, we already know what the time reversal operator does. Time reversal acting on psi k sigma gives you this factor zeta sigma psi k sigma. Notice that whatever we have here is a bunch of continuous Lorenz transformations. These are definitely unitary operators. So the factor xi sigma can move all the way out. And just as we did a while ago, we recognize R of p hat R2 as R minus p hat e to the plus minus I pi j3. This e to the plus minus I pi j3 once again can commute right across B and go and hit the psi k sigma, giving rise to e to the plus minus I pi sigma here. Note that we don't have a change of sign to e to the minus plus I pi sigma simply because J3 now is acting on psi k comma plus sigma, unlike the previous case for parity. So putting all this together, what we see is the following. The effect of time reversal acting on psi p sigma is to produce a state psi with a 4 momentum, which is actually the parity reversed 4 momentum. So the upshot of all this is time reversal acting on psi p comma sigma actually gives rise to a state psi with a 4 momentum curly p comma sigma and J3 eigenvalue plus sigma. Note that the new 4 momentum is parity acting on the original 4 momentum and not time reversal acting on the original 4 momentum. But that's to be expected anyway, because time reversal acting on the original 4 momentum would have given you a negative energy state, which is really not what's going to happen here. And then you have an overall phase factor zeta sigma e to the plus minus I pi sigma. Once again, rather abrupt change in sign in the phase factor when you cross the xz plane is simply an artifact of the coordinate system chosen. So this is what time reversal does to an arbitrary energy momentum eigenstate. We are going to find these results for capital P and capital T acting on psi p sigma very, very useful when we talk about parity and time reversal symmetry or their breaking in later sections. For the time being, let me just introduce you to a very nice consequence of the fact that time reversal is an antilinear operator, which follows directly from what we have written down here. We are going to take a look at what T squared does to the state psi p sigma. And for this, we are going to consider both massive and massless particles. For massless particles, as we have just seen, T psi p sigma is simply zeta sigma e to the plus minus I pi sigma to psi curly p comma sigma. For massive particles, the action of time reversal is slightly different. And this is something we described in the last section. T acting on psi p sigma turned out to be an overall factor zeta times minus 1 to the j minus sigma times psi curly p comma minus sigma. Now, let us look at what T squared does to psi p sigma, and we are going to see this for both the massive and the massless cases. For the massive case, T square acting on psi p sigma is simply T acting on zeta minus 1 to the j minus sigma times psi curly p minus sigma. Now remember, T, the time reversal operator, is an antilinear operator. So this zeta comes out of it as zeta star. Minus 1 to the j minus sigma is actually a real number because j minus sigma is always a positive integer. This is something which we actually focused on as to the reason why we introduced this extra minus 1 to the j. And so that will come out intact. Now you have the time reversal operator acting on psi curly p comma minus sigma. And that, of course, is going to give you a factor of zeta with minus 1 to the power j plus sigma. It's j minus whatever the spin component is, but the spin component here is minus sigma. And what happens to a state psi? Curly p gets another curly p to act on it, and curly p square being identity, you're back at p, and the spin minus sigma reverses to become plus sigma again. So the upshot of all this is, you are back to the same state psi p sigma with an overall factor in which zeta star and zeta, being complex conjugates of each other, as well as the fact that zeta is a pure phase, magnitude 1, cancel each other out, and you are left with minus 1 to the power 2j. So t square acting on psi p sigma is actually psi p sigma back with minus 1 to the 2j as an overall factor. Remember, j can also be half of an odd integer, so minus 1 to the 2j is not necessarily always plus 1. And that is going to be a very important point in what is going to come. By the way, j differs from mod sigma by an integer, and therefore 2j differs from 2 mod sigma by an even integer. So these two factors are actually one and the same. The reason why I write this in this fashion is because it's going to make the connection with the massless case even clearer. Notice once again that it's the antilinear nature of t which is important in this derivation. For the massless case, we will just apply t square on psi p sigma. We know that psi p sigma with a single t acting on it gives you zeta sigma e to the plus or minus I pi sigma psi, and in this case the momentum changes to curly pp, but the spin sigma stays the same. Now when t acts on this again, you will have to first move out this factor, which of course gets complex conjugated, so you get zeta sigma star e to the minus plus I pi sigma. That's the complex conjugation. Now t gets to act on psi curly pp comma sigma, and that gives rise to a phase factor zeta sigma e to the minus plus I pi sigma. In case you're wondering why the sign here is different, remember you get a plus or a minus sign depending on whether py, the y component of the spatial momentum of the state, is positive or not. Now, originally, you had a state psi p sigma for which py was either positive or negative. The positive or negative signs gave the plus or minus sign here respectively. That of course changed to minus and plus because of the complex conjugation due to the antilinearity of t. But now this t is getting to act on a state for which the form momentum is curly pp, that is, the parity of matrix has acted on the form momentum. This of course has changed the sign of each and every one of the spatial components, and in particular it has changed the sign of py. So if your original py were positive, now in curly pp the py is negative and vice versa, which is why you have a flipped sign here. Whereas you had e to the plus or minus I pi sigma here, depending on whether py were positive or negative, here you would get e to the minus plus I pi sigma. Now once again, zeta sigma being a pure phase cancels with its complex conjugate, and you are left with e to the minus plus I pi to the power twice sigma. And that you can easily write down in the form minus 1, that's of course e to the minus or plus I pi, to the power twice mod sigma. Note that sigma can be an integer or a half integer, but the difference between sigma and mod sigma could be either 0 if sigma is positive or twice sigma. So 2 times that, the difference in the exponent is 4 times the magnitude of sigma, which is always an even integer. So these two quantities are always the same. So the important point is, for both massive and massless particles, the action of t square and on psi p comma sigma is minus 1 to the power twice mod sigma psi p comma sigma. In fact, for a massless particle, the J3 component is often called its spin, so you could just say that t square acting on psi p sigma is psi p sigma back with a minus or a plus sign depending on whether the particle has a half-odd integer spin or an integer spin. Now this gives rise to a very important consequence. If you have a system which has an odd number of particles with half odd integer spins, so that you get an odd number of minus ones from each one of them, as well as an arbitrary number of integer spins which contribute plus 1 anyway, so we don't really care how many there are, then the wave function for such a system would satisfy the following condition. T square acting on the wave function will give you the wave function back, but with a minus sign. Now, the Hamiltonian for such a system with time reversal symmetry, of course, commutes with T. So if psi is a H eigenstate with eigenvalue E, it is obvious that T psi will also be an H eigenstate with eigenvalue E. But the important point is that leads to two possibilities. One is that the state T psi is simply a multiple of psi. But if that is not the case, then the eigenvalue E must be at least doubly degenerate, because psi and T psi would then be two independent states with the same energy E. Now consider the situation that we have talked about just now. A system with an odd number of half-odd integer spin particles. Then, if T psi is actually a multiple of psi, that is T psi is alpha times psi, remember that because T is a unitary operator, anti-unitary is also unitary, that is norm-preserving, T psi must be the same as psi, and that leads to the conclusion that this alpha must be a pure phase factor. But then, T square acting on psi will be T acting on alpha psi. Antilinearity of T means the alpha will come out with a complex conjugation, alpha star T psi, and T psi will of course be alpha psi again, so you get alpha mod square psi. And since alpha, as we just concluded, is a pure phase, this must be equal to psi. So notice that our result that for system with odd number of half-odd integer spin particles, T square must be minus 1, actually rules out the possibility that T psi is going to be alpha psi. If T psi had been alpha psi, T square psi would have to be equal to psi. So for the kind of systems we are talking about, T psi equal to alpha psi is not possible, and hence the other possibility is the one that comes up. The eigenvalue must be at least doubly degenerate. This result was established in the year 1930 by H.A. Kramers for the special case of the Bright equation, which is actually an application of the Dirac equation for multiple particles in electric fields. It was Eugene Wigner who later showed that this is a consequence of time reversal invariance and is thus much more general than the rather limited setting which Kramers proved the result in. Now this is a rather neat consequence of time reversal symmetry, which has important consequences in spectroscopy and other subjects. But the important point here is that all we needed was the basic mathematical structure of the time reversal operator, in particular its antilinearity, to come to this conclusion. We will see deeper consequences of parity and time reversal symmetry later when we talk about interacting systems in more detail. But for the time being, this is all we will have to say about parity and time reversal. In the next section, we are going to take up the question of projective representations, that is, representations up to a phase factor. Of course, you can always have such representations, but in most situations, as we have seen, we could get rid of those extra phase factors by redefining phases of the system. The question that we are going to be interested in, at least for Poincare transformations, is it possible that there exist some representations for which you cannot get rid of this extra phase simply by redefining the phases of the states? That question will lead us into some deep issues about topology and representation theory. But that is going to be for the next lecture.